I just wanted to show you something really quick that this just came to my attention this morning. So I haven't even made a slide for it yet. This is a paper released just yesterday. And we're going to, like later today, we'll see some examples of this kind of work. So like image to image mapping. But this is like super mind-blowing, so I wanted to share it with you guys. Image to image translation. So a lot of tasks in machine learning are sort of like taking one image and mapping it to another kind of image that is interesting, that is important. So like for example, I'll just show you a few of these samples. Let me get let's look at this. So like for example, you might go from a map, like maybe you want to take a map and you want to parse it into a data structure that shows where the roads are, where the buildings are, things like that. Or maybe you want to do more generative tasks. So we'll see like some generative stuff like this, where you go from a drawing, like a segmented drawing, into an actual generated photo. This is not real. This is like a generated photo of a building from a drawing. So you create the drawing, and it creates a photo to match it. Or you do colorization, right? So this is a colorization, where it goes from the black and white to a color photo. Or you draw edges, and it creates a photorealistic sort of rendering of the thing that you drew. The really cool thing about this, and maybe this will make more sense after the slides from today, is that it does so that this particular framework and they released the code for this, it does so without explicitly writing or creating some sort of a loss function. So we talked a little bit about loss functions in training neural networks. A loss function kind of defines the objective of the task. Here, they don't even do that. They just give tons and tons of image pairs, and it learns the objective itself. So it's like one generic approach to learning different kinds of, sketch to drawing, image to map, aerial to photo, things like that. So this is a generated street scene. So pretty mind-blowing. This always happens in my classes where something mind-blowing happens during the class. And sort of we have to update our approach. So maybe and I'll just really quickly show you a few samples. So they have code for this, so we could potentially use it here. I'd love to actually see if someone might be interested in working with this code. It looks like it's pretty well made. It's using Lua, using Torch, which we haven't talked about. We'll mention it later today. I'll just show you just a few more samples. So these are so this goes from like a Google Maps image to a generated aerial photo. And this is the real one. So this is an actual photo that the map is generated from in Google. And then this is a generated aerial photo that looks kind of gnarly, but it's pretty cool that it basically just goes from this into what appears to be like a very close to realistic looking satellite photo, and it can go in reverse as well. So here's some more examples of this. I guess we can kind of zoom in. So the ground truth is on the right, and the generated one is on the left. And then I'll just show you a few more. So this is the reverse. So going to taking the satellite photo and generating the basically Google map. Right, so this is the ground truth, and then this is the generated one. You see the arrows are sort of weird. Like it doesn't really know which way the streets should be going. So it doesn't quite figure that out yet, but that's pretty impressive. So this is a way to maybe do, and maybe this is actually like, here, one of my first instincts would be to look at this and think about something very sinister. So now you can, so many places in the world are undocumented because you can't, Google Maps cars haven't managed to make it there yet. But here you can actually just look at satellite imagery, which we have tons of, and generate a cohesive map of the place. So again, a totalitarian's best friend, I think, is something to be considering. This is reconstructing the segmentations. This is the kind of stuff that self-driving cars try to do to understand the scene. So here they're segmenting street views. This is going day to night, so it's like making the nighttime equivalent of the photo. So this is the ground truth, and then this is the generated. This goes from sketch to bag. So here are real bags, and then the one in the middle is the generated one. So you can imagine this is like this could be a cool art tool. You make a little sketch, and it auto-completes a photo for you. That's an actual photo. So this is what they use to evaluate it. So they'll take the sketch from an actual photo and see how the reconstructed photo compares to it. Well, no, once you have a model, you can draw anything. Yeah, you just don't have, you may not have something real to compare it to, but you can definitely draw things.
The ground truth in this case was also part of the training.
Yeah, probably. Yeah, I haven't read the paper yet. I just saw it this morning, but probably, yeah. Shoes. You guys want some shoes? Yeah. Some are better than others, of course. More bags. I guess they really like bags. Or no, what are these? Yeah, these are bags, I guess. More shoes. These are gnarly, right? I want these. I want these shoes. Super colorful. I'm not sure what the difference between some of them are. I haven't read the paper carefully. Street scenes. Okay, house buildings. Check this out. So you make the blocks, and then this is the ground truth from this generated from, and I think the best ones, the state-of-the-art ones, are over here. Pretty impressive. Oh, no more. More of this. So generating satellite imagery. Okay, I think these are with patch size variations. What is the deal here? Oh, maybe they're changing the size of the patches. So this could be a way to like make tools, for example, for, let's say you're an industrial designer, and you're working with like, designs like this, and you want to go, I want the windows to be bigger. So you make the patches bigger, and then it will generate a new image for you. So I would imagine that this is the sort of stuff you'll see in design software in the near future, I think. Not just yet because it's in the research, but I think it's getting close. Okay, so yeah, I just wanted to share that really quickly. So anyway, besides for that, I was thinking more or less the plan for today can be, we can do a little bit of, so there's two things I want to do in the morning, and we can do them in either order, and we can maybe just take a vote. One is, like we should break out and kind of start to think about ideas. I think a little bit of that started to happen kind of naturally yesterday after we did the practicals. So that's something we should do. And also, I wanted to show you two more applications that could also actually be informative for the discussion, which are I showed them briefly, but I can actually show the tutorial how to do it. One is making your own image classifier in real time using a ConvnetOSC and Wekinator. So that's something that I showed you with the coffee cup and the croissant. And then the other thing was audio t-SNE, so segmenting audio and then creating a t-SNE map, a layout of all the samples. Those are all things that are that can be helpful here also. So we can do those in either order. It's up to you guys. Maybe I think there's some want to kind of start brainstorming, and then I suppose I think we'll still have time after that. But then after that, I have some slides for some stuff, some deep learning stuff. So we'll kind of get into this sort of stuff that we were just looking at, things of this nature, including, deep dream and style transfer. They're all image-to-image translations, right? So style transfer, which I suppose I showed briefly on the first day, is an example of taking one image and producing an output image which has some particular objective. So all of these are examples of that. So we'll see some more, some of the ones that kind of started to gain traction with artists and whoever last year. And then I'll show you some of the software that you can use to actually use it, which we probably won't really do a tutorial, but I'll just show online where it is, and then we can talk about who might be interested in using some of the deep learning stuff. Okay, what order should we do this in? Should I do the tutorials first, or should we have a brainstorm? Like, you guys want to do a so raise your hand if you want to see the tutorials first, and then do a brainstorm. Raise your hand higher so I know. Okay. Oh, okay. Most people, it seems. Okay, so let me do that first, and then it'll take, I suppose, maybe like 40 minutes, something around that time, and then we'll break out for discussion. Does that make sense? Cool. Okay. So the first thing I'll show you is Wekinator, to making your own image classifier using into Wekinator. And I guess the way we can do this is with processing first as the output, and then we can maybe attach that to some actions. So just remember, like, I'm going to open the OpenDot slides. So remember, one of the last processing sketches we had was, we can do this with sound, but let's do the simple one. I'm going to actually even better, I'm going to copy this. 3. Okay, and then so remember I showed you guys briefly this tool called ConvnetOSC, which I built in openFrameworks. It's available for you guys to use. So it will send, let me close it right now. It'll send Convnet activations over OSC, which you can send to Wekinator. You can send it to wherever. Obviously, it can be used for other things. Although I don't know what you would send 4096 numbers to besides for Wekinator. So remember, we had something like this, which would color, this would color the screen depending on where you had the mouse. This is something that we did in the first day. I'm going to repurpose this and instead do something using ConvnetOSC and Wekinator. So here I'm going to open Wekinator and ConvnetOSC, and I'll just quickly, and remember, all the source code for this is online, so you can modify it, you can do whatever, you can attach things to it. But if you want to just use it by itself, you can also do that. So remember, when you hit the spacebar, it turns green, it starts sending. And it's sending right now to localhost. Again, we can change this. We can make it send to each other, which is something we might want to do. And sending to /wek/inputs, and sending 4096 values. So for the most part, it should be straightforward, kind of in how we hook this up with Wekinator, although I find that making a few modifications are actually useful. So just remember, for those, so we didn't, we looked at Wekinator 2 days ago now. I'm going to turn this off. So we'll start listening on port 6448, right, which is where we're sending the values to. And we're sending 4096 of them. So that's how much it's sending to /wek/inputs. And let's, for now, just for the sake of saving time, we'll do one output. And we'll make it, we'll just make it a classifier, right? And maybe we'll make it a classifier with, how about 3 classes, just for fun. And there's one thing that we need to do to make this a little tractable, which is changing the learning algorithm, which we have to do here. So here's the problem here with, in this case, Wekinator asks us, by default, it uses a k-nearest neighbor learning algorithm, which means that it will save a whole bunch of samples of, of our 4096 values and the class. And then at runtime, it will just look for the closest one. That's sort of not ideal because we might have a lot of samples to look through. It is really fast to train, but maybe not the best approach to the problem, because it doesn't, we can think of sort of It actually might even be best, who knows. But what I'm going to do is I'm actually going to choose a support vector machine, which is going to create a classifier. And a support vector machine, just because we haven't talked about it carefully, you can think about it as it's basically very much like a neural network. It takes as its input a vector of an input variable vector, and it produces some output vector of outputs, labels or regression or whatever, and or support vector machines are usually used for classification, which is what we're doing here. And it may take a while to train, so I think we might have to choose a couple. This happens a lot for me. Sorry. Does this happen to anybody else where it starts to crash a lot? 4096. 1, 3. Okay. And I think it makes sense to possibly edit the support vector machine, and then maybe we can. So yeah, this is something. Okay, this is some more advanced settings. You may not necessarily need to work with these too much. I'm just kind of looking for things that might make it a little faster to train, but I think this should be okay. So let's just go with this. Okay, good. So now I'm going to record a bunch of. So let's create an image classifier. I want to use 3 objects to train the classifier to recognize them. So let's use. I'm going to use my phone. What's something fun I could use? A roll of duct tape. Thank you. A roll of duct tape. A glass? Yeah, let's use a glass. Perfect. Or scissors. Well, let's go with the glass. Okay. Okay, so this will be class 1. I'm going to start recording on the Wekinator side. So now Wekinator is recording for class 1. And as soon as I hit the spacebar, it will begin to send values to Wekinator. So let's make class 1 the phone. So I'm going to put my phone in front of it. I'll kind of get it ready. And it always turns on automatically when it sees light. Okay. Okay, so now I'm going to begin training, or rather not training, but collecting samples. So it's receiving, maybe kind of rotate it around so it gets it in as many positions as possible. Sort of move it around, give it lots of samples. Okay, cool. Stop. Okay, so that was class 1. We got 73 samples. Now I'm going to do class 2, and we'll make the duct tape class 2. Okay, so now class 2, start recording. It might also pick up part of my face as this classifier, right? Okay, just getting more samples, moving it around a little bit. Okay, good. Now I'm going to switch to class 3 and the glass. Okay. Okay. So now I will stop recording and we'll hit train. Now this may, oh, that was fast, great. Sometimes, I guess for regression it takes a little longer because it uses, it depends on the learning algorithm. The support vector machine is pretty quick. Okay, so now I'm going to begin running it and we'll begin to send values. So first of all, so just notice the class that it outputs. I'm going to zoom in here. So just pay attention to the class that it's outputting, which is right here, right? So phone. Oops. Right, so class 1, class 2, class 3, 2, 3. What if we try to confuse it? Like the phone is overpowering the glass. There we go. Okay, so again, like we can think something cool to do with this. Maybe we could save time, or I could try to do something like fun with this on the spot potentially. So like so think of some of the things that we can do with this, right? You can perhaps trigger, with processing it would be pretty simple to make this be a sound trigger. So which is something that we could quickly do. We can make an example for this. We could have it, again, like we could have it triggering samples if you're a musician. Again, I like to use the music example because that's usually the easiest to start with. You can have it be, so like if you're a Maximus P user and you use it to control various sort of generative workflows, then you can have it be in the control flow of your program. So something responding to a particular image class. So those are all possibilities, right? So simple thing with the classifier. You can also, of course, we just did this with regression. With classification, but this could also easily be repurposed for regression also. So you can have it control, how much of the roll of tape that it sees, and so on. Okay, so that's ConvnetOSC. Maybe later if we have again, like later today, if we do a sort of more practical stuff, we can kind of try to hack with this and just make a few like prototypes that do different things. Okay. So let me save that and exit. And then the other thing I wanted to do is show you, show you audio unit OSC. So if you go to GitHub and go to ML4A GitHub, and you go to the OFX folder, this is an openFrameworks application, but you don't necessarily need openFrameworks to use it. I have builds of it in both Windows and in Mac. Of course, if you just get the binary, you can't edit it, so it just does one simple thing. But for those who want to play with their own audio sets, that's sufficient. You can kind of like use the thing to see some of your audio and understand it a little better, understand its distribution. And for those who want to work with the code, it would be pretty easy to do. So one of the apps in here is called Audio t-SNE Viewer, Audio t-SNE Viewer. I don't have very much documentation yet. This is one of the things that I've been planning to do after the workshop, or maybe during it, is improve the documentation. But this will just basically describe how to make your own audio t-SNE map. Just to remind you guys what it was. Actually, I have to quickly run it here because I have. Let me just put it in as a slide real quick. Audio t-SNE. So I'm just going to run this. Okay, while that's building, I'll just mention, so you can clone the app, and then this describes how to analyze a collection of audio, and you have two options. One is to analyze a folder of audio samples, which really ought to be kind of short. So here we go. You guys can hear all that, right? I don't have the sound plugged in at the moment. Right, so this is a layout of samples. This is a drum kit. Thank you. Sorry? Oh. Okay, cool. Yeah, so you guys can hear. We looked at this really briefly yesterday. So this comes from a drum kit samples. That's not too bad. And that's one option you can use. And the way that it works is that the ML4A OFX repository comes with two folders, apps and scripts. And scripts are basically Python scripts that do the analysis for you. So they'll do the analysis. It's a command line script that you just run in terminal. You do the analysis. It will run. It will generate a JSON file that has all of the data, and then you simply load that in openFrameworks. And if you go to the apps folder and you go to Audio t-SNE, you'll see that it gives you instructions exactly how to use it. And as I said, there's two options. One is on a single sample of audio, on a folder of samples. And really, they have to be short because the analysis is kind of optimized for analyzing, the timbre of a very short piece of audio. It doesn't really make sense to do it on songs just yet. That would probably require a little bit of a different analysis. And then the other example is to give it a single audio file, and then it will actually automatically segment it for you and make samples, make small samples, and put them into a folder. And now this is shown how to do that here. So for example, I have the drum samples they are here, right? So I'll just show them to you. So all of the sounds you were looking at, this is some sample kit that I downloaded online. I don't even remember where from. So bass drum, right? That's pretty nice, huh? Right, so these are all these drums, and they're actually already kind of organized for you. But there's lots of them in here. I have a few more audio sets that we might be able to make use of. So I have this sample kit of nature effects. So like ice, for example. Oh, that's crunchy, right? So crunchy. Metal. What was that? Monsters. Let's hear the monsters. So I think these are like what Foley artists use to make movies like Jurassic Park, I think. So that's something that's available. So you can, if you have a folder full of audio, you can lay it out with sample t-SNE. There's a lot of other things you can. So then, like, I'll give you some ideas. So for example, one of my students in our class in Berlin used it to analyze like 50 years of noise music, and he put it on a layout, and then he made this. He made a program in openFrameworks that would keep the cursor. The way I was running it was with the cursor, and he made it so that it would kind of roam around, and then when it would kind of roam around, randomly, or you can control with the mouse, and then within a small radius around it, it would do a sort of granular synthesis. So it would play many of the samples, kind of overlaying them and creating a sort of texture. So one region of the t-SNE is it will sound kind of more or less homogeneous. And so you can create a granular synthesis over it. So it's a neat way of making music. I've also used it to segment an opera. So I have that, but it's actually not working because I think it's not finding the right path. I have to fix that. I'll maybe show it to you after lunch. But you can segment an entire audio track and then lay out the different parts of it. So those are all things you can do. The way that you would run this, again, so you would go to like a terminal, and so you can go to wherever you have the ML4A OFX folder. So here we are. This is the folder. And then you can do this. So basically, it's running this script called t-SNE audio.py, which is inside the scripts directory. So you see here's t-SNE audio.py. So you go Python t-SNE audio.py. And here it will ask for an input directory. So input dir. And then you give it a path to whatever folder you want to. If you want to analyze a folder, you would do it this way. So let's say I wanted to do the drum samples again. Oh, but be careful. I have a space in there. So if you have a space in the folder, make sure you put quotation marks around it. Otherwise, it will split up the command incorrectly. And then output file is where to put the JSON. So here I'll be like, okay, output file, and I'll put something on a desktop. I'll be like, okay, so here's my desktop folder, and I'll make, drums.json. So it's going to make a JSON file. So if you run this, and if you've installed all the libraries that we've already, if you've installed them locally, like not through Docker, you should be able to do this now. It's just using librosa mainly. So you would do this, and then it will grab all the samples, and then it will start analyzing them. So here it found 2,121 samples. It's analyzing them, and it's doing so really quickly, right? So it's going to get through this in just a few seconds. Once it's analyzed all the features, it has a feature vector for each of the samples, and it will run a t-SNE on them, and then generate the results into a JSON file and give it back to you. So let's just really quickly let it do its thing. And then actually, while it's doing that, I can edit this. I can edit my demo. This is a little different from the one that's online. I think this should work, right? So yeah, if I do, instead of this, I'll do the drums.json, right, so desktop. So here I'm just choosing the file to load, and it's going to be drums.json. I think that's what we called it, right? So this will just do the t-SNE first. And while it's doing that, I'll just make sure, what did I call it? Drums.json, right? And yeah, it'll do its thing in just a moment. And then I'll just, I'll kind of show you. Well, you've already seen this because we're analyzing the same folder of audio. So maybe I'll do a separate one while we're having the session. In any case, this is how it works. And if you have any questions about it, you want to use it, please let me know. So while it's finishing up, I'll just kind of say, okay, so maybe now we can kind of figure out a way to organize a brainstorming session. What do you guys think? Like, should we kind of break out into groups? Maybe we could take a vote. Would it make sense to break out into the clusters? Or should we have more of a roundtable type thing? So what do you think, like break out into clusters? So let's do that. Let me just quickly also just show you, because I quickly did this while we were here. I took the song Bohemian Rhapsody. You guys know Bohemian Rhapsody? So, oops. Bohemian Rhapsody. Everybody know this song, right? So I used the software. I analyzed that track. It analyzed it and found all the onsets, segmented it, and then and put them into a folder, a directory of samples called right here, Bohemian samples. And then also it generated the t-SNE map in bohemian.json. So let's really quickly see how that came out. So here I'll compile it. Now it's going to run bohemian.json.
What is inside the JSON? Coordinates of
I'll show you. It looks like this. So here it's just a JSON file that has all of the paths to the individual samples and a layout, a point in the layout. So like, yeah, exactly, for each of the tracks. So it just has all the info that's needed to generate the map and display it. So here it is. Piano cluster. Guitar. so on, right? So just something that you can do.
Seems like a lot of these samples were all ordered almost on the line.
Sometimes, when they're very close to each other, they'll get into, they'll find a layout that's kind of like that. Yeah. Yeah.
One thing I thought, we didn't see anything about like feedback neural networks. I mean, like
What? Sorry. What kind of?
like feedback inside neural networks. Like if I'm not wrong, the deep dream images.
Yeah.
They take some kind of
Yep.
product of the neural network.
Well, Deep Dream can be, so if by feedback you mean like taking the output of a neural network and sort of making that the input again, you can, yeah, so Deep Dream is sort of like, yeah, Deep Dream kind of works in iterations where you'll, well, I mean,
How do you train new images?
it's not feedback technically, but the way I'll actually describe this afternoon how Deep Dream works. But it operates on the same image, multiple times, iterations, iteratively.
It'd be nice to do a very kind of similar thing to the audio. To get like.
Yeah, you and lots of scientists are also interested in it, but it's just not there yet. The audio Deep Dream is not yet. It's getting close, but not there. Yeah.
Something similar. I mean, I'm interested in getting like new, kind of like a similar effect.
Mhm.
So starting from an image and see, other image patterns inside that image and kind of produce something new out of that.
Yeah.
So like I have the same concept. I know that maybe technically it's still in the research phase,
Mhm.
but is there any way of getting some kind of similar effect, if you get what I mean?
So from audio.
From audio, kind of see patterns that you're not able to see and bring out a new synthesized sound.
I mean, the only way those things are done really, as far as I understand right now, are using not machine learning really, but more, or at least not machine learning by itself, but using some sort of like manual feature extraction and a lot of hand engineering. Like there's not, so like in the analogous sense would be something that kind of does it autonomously with a neural network, but it's not really, I haven't seen anything like that. I mean, there is stuff that, obviously we're talking in about something very abstract, so there can be a lot of things that qualify. But, people do a lot of analysis and then generate, and then, use that to create, let's say for example, I've made like a stuttering effect. You'd find some onset and then it'll play it back like, with a sawtooth wave or something like that. But that's not really, machine learning. That's just kind of traditional. That's a pretty traditional technique. Doing that with machine learning, I haven't seen yet. The closest thing that's getting to stuff on the audio level anyway is wavenets, and I'll be showing you that maybe either later today or tomorrow. But then otherwise, yeah, it hasn't been fully developed. There's also some work like the CSAIL, the Sony, I think Sony group, where they used machine learning to write a Beatles song. But really, like, it's a little misleading because what they did was they used an AI to write the chords and the melody, to kind of compose it. But then they also had human beings actually arrange it and play it. So it's not fully autonomous.
Even that, the result is not such.
It sounded pretty cool. Sounded like a Beatles song, more or less. Yeah. Yeah. So yeah. Yeah.
It's really great if you want to be connected to the emotion of the baby, for example, from their face and recognize how the emotion then connects something to that react to their emotion and keep them being emotional. That you need machine learning.
Yeah, like.
I mean, it's just not just recognition and reaction. We can do with that, of course, but I was thinking more being connected to the topic of the work.
So for example, like really the machine learning comes into play when we don't know how to program the function that we want to create. So there, you can think of functions where maybe machine learning is not necessary because you can think of a way to implement it using techniques that you already know. So for example, if you want to detect motion, you don't need machine learning for that. You can just look at frame differences in video frames or something like that, detect how much motion there is. But for a task like detecting emotion on someone's face, that one's really difficult to do without machine learning because how do you program that? You know, like we have a classic technique for motion, just subtracting one frame from the other and seeing if there's a lot of difference. But then with emotion, it's like, okay, are you going to compute all these pixels and then figure out what they should look like for a particular emotion? So it really comes down to like machine learning whenever you don't know how to program it by hand. Yeah. Should we maybe break out into our clusters now and then have some sort of more focused discussion? Does that work? Does that make sense? So I'm gonna go ahead and turn off the recording, and we'll kind of like we'll regroup in a little while, or I don't know, maybe in like I don't know how long we should. How long do you guys think we should sort of spend a half hour or something, or 45 minutes, or maybe like we can decide as we go? Let's just decide as we go. It's okay.